Now the next level, taking this idea further, is to be able to do very sensitive quantitation. And the tool of choice for that is ELISA. And in biopharmaceutical development, the vast majority of ELISAs are done using 30 to 40-year-old microplate technology. In the microplate, the well itself, the wall of the well, is used as the stationary phase, the solid phase. And the capture antibody is immobilized on that. And there's a millimeter scale diffusion path that the target molecules have to cross in order to reach that binding surface and be measured. And that's a very long distance for a molecule to diffuse across. And so that's why these assays typically take anywhere from half a day to a whole day to do. There's a lot of waiting around for this diffusion to occur. What we've done in the AssayMAP system is pack cartridges with relatively large, non-porous beads that have a very similar surface chemistry to the microplate well. So because they're non-porous, the surface area is very similar to what you have in a microplate. But now the diffusion path is just the space between the beads, which is not millimeters, it's tens of microns. And so diffusion is no longer a major barrier. And the entire assay from start to finish can be done typically in about half an hour or so. So although this is an ELISA, it actually has exactly the same kinds of steps that we just showed for purification. So we initially coat the beads with the selective antibody. We block the remaining non-specific binding sites. And then we expose it to the sample, and the target binds to the bound antibody. We then come in with a second antibody that has an enzyme label linked to it, a conjugate, and then we come in with a substrate for the enzyme that produces a colored product and gives you your readout. And in the case of the AssayMAP system, the substrate is actually pumped through the column, and the colored product is simply collected in a microplate and read in a plate reader the way you normally would for a standard ELISA. And we can actually dial the sensitivity, or the signal strength, if you will, of the assay by changing the flow rate through the cartridge. It's kind of cool. So here's an example of this. This is a typical ELISA that's used in bioprocess development, actually looking at protein A itself that might leak off the process column and contaminate the final product. So you need a very sensitive assay. This is typically, the specifications are in the parts per million level, and so you need to be able to get down to under a nanogram per mil concentration. And this is, we just simply took commercial reagents from Cygnus Technologies, a well-known vendor in this area. And you can see the green triangles are actually from the package insert for the product, the results in the microplate format. And we were able to get essentially identical results using exactly the same reagents on the AssayMAP, except that the assay takes about half an hour instead of a day to do. And the CVs, the analytical precision, is also excellent here, well under 10%. Now, you can also extend this idea into much more complex workflows. One of the ones that we have been working on collaboratively with Prozyme, and that they've commercialized in a product called GlycoPrep, is N-glycan profile analysis. And what you're doing here is taking glycoproteins, selectively removing the glycan carbohydrate groups, fluorescently labeling them, cleaning them up, and then they're analyzed subsequently by mass spec or capillary electrophoresis or some other method. So this is a very complex workflow. Our method has actually 15 steps in it. We denature the protein, immobilize it on a solid surface. We come in with an enzyme, PNGase F, that selectively clips off the N-link glycans. Then in the solution phase, after we've eluted off the column, we've now separated the protein from the glycans. We fluorescently label it, and then we have a separate cleanup cartridge that removes the excess fluorescent label and salts and everything else so that it's ready for analysis. So the current methods here actually are really only done manually. There are a few pioneering souls that have been trying to automate current methods, but it's really been pretty unsatisfactory. And a typical method takes 3 full days to complete on 30 to 50 samples. With the AssayMAP-based method, it can be manual or automated. One of the big things we've done is eliminate drying steps that are normally done in this. And we can do the entire assay on 192 samples in 3 hours. This gives very comparable results to the standard methods. These are two typical proteins, IgG, very common, and alpha-1 acid glycoprotein. You can see the profiles are very similar. It's also extremely reproducible. People typically have CDs of 30% or more in these. These are actually 12 overlaid HPLCs traces. You basically can't tell that it's 12. And on the right are the 6 major peaks, the actual percent of the total peak area, and it's extremely reproducible. Now this workflow can actually be made even more sophisticated because most of the samples that you're dealing with are either coming from cell culture or serum. So you first need to purify out the target glycoprotein from that crude sample before you can even do this glycan analysis. So one of the things that we are working on right now is combining the purification with this, the rest of this workflow. So for example, for an antibody, we can use protein A to selectively pull the antibody out of the crude sample, wash away all the impurities, and then do the whole rest of the procedure using the antibody immobilized now on the protein A itself. And here's some results with this. A is the trace that looks familiar to what we saw on the last slide with the antibody just in buffer. B is in a cell culture supernatant, and you can see the traces are essentially identical. C is where we took that same cell culture supernatant with the antibody on it and loaded it on the hydrophobic cartridge that binds all the proteins. And so you can see there are a ton of other glycoproteins in the cell culture supernatant, and the antibody trace doesn't even show up in there. So this shows you that the purification is working. And indeed, we took the cell culture supernatant without the antibody, ran it over the protein A cartridge, and you can see there's basically no background binding whatsoever. So this is now a highly integrated workflow that combines purification and digestion and all the rest of this processing in one integrated system. So the last thing I'd like to touch on is because we have a high throughput chromatography system, we can actually use this for doing chromatography method development. When you're doing, for example, ion exchange chromatography, one of the things you need to look at is optimizing the pH and salt concentration of the wash and elution steps. So if we look at this, we might want to, on a micro scale, using a very small amount of sample, look at a grid of pHs versus ionic strength for the wash step, for example. And rather than show data here, kind of a picture is worth 10,000 words. This is one of these rows, and this is, we're binding a protein called cytochrome C, which has a heme group in it, so it's a very deep red color, and we can actually see it on the cartridge. And on the left is a wash with 0 molar salt. I forget what pH it's at. And we're increasing steps up to 100 millimolar salt on the right. And you can see very clearly on the left, the cytochrome C is very tightly bound after the wash on the top of the column. And on the right, it's almost all washed off at the higher salt concentration, and there's a nice gradation in between. So even though this is a 5 microliter packed bed, it's displaying true chromatography performance.